Okay, let's start. So it's nice to see some of you once again. I already recognize some names. So you will listen for my presentation one more time. So my name is Anna, and I'm excited to introduce you TECA. TECA stands for Technological Empowerment in Creative Arts. It's a project sponsored by European Union. So we connect artists across borders and help them to create the future of digital arts in Bosnia, Serbia, and Romania. Next. Sorry. Yeah. So the project is driven by 3 partners, Iceberg in Romania, FabLab in Bosnia, and Polyhedra in Serbia. So this week we continue doing the workshops. They're all take part online until 18th of March. And after that, next week, you will all receive more communication regarding the next steps of the projects, but we will be running matchmaking events also online, where we can match you with some other artists, because project collaboration requires international projects. So you should have at least one partner from one of the 3 countries that participate in TECA. And we are looking for 9 projects in total that we will be mentoring and provide all the help that is needed for you in the next few months. So by the end of the month of May, you can develop a prototype and build a project that can be showcased in one of our maker fairs in 3 different countries. So, oops. What else? I think I said, yeah, almost everything. Yeah. So I'm kindly asking you to join the Creative Nexus platform. So it will start working this Friday. Now, even if you registered, you may notice that it's not yet. You can enter your account, so it would be possible at the end of the week, and then you will see more information there, and there will be also call for projects, and you will be able to post your ideas and find all the other artists that would like to participate in the project. Yeah, and maybe find a collaborator there or post your own idea there. So yeah, I think that's pretty much it, what's going on right now. So yeah, I again asking you kindly to join the techalab.eu, and then we'll start from there, and we'll give you more information in about a week time with all the deadlines regarding the submission of the projects. And yeah, now I'm passing the stage to Emir, and he's gonna teach you some stuff about electronics and photonics today. Can we? I don't think. Can you? I'm not sure if the sound. Yeah, there is no sound, so. Please.
Is it better now?
Oh yeah.
Okay, good. I was on the wrong microphone. Good. So thank you, Anna, again for the introduction. I will present you some photonics and electronics for creative arts that I prepared for you as a small presentation. I'll start with sharing the Okay, can you see my screen? All right, good. So we have basically two sessions. One is on lighting design and other is on fundamentals of electronics. I will try to keep it relatively brief, and yet I hope you will learn something today. So let's see with lighting design. So who is in charge for lighting design? So who is the person that designs lighting on for a building or an office or a hospital or a road, a tunnel, or whatever an object can be, or a living room? Is it architects or is it engineers or interior designers? Maybe. Well, it depends mostly on the project, but we all must know the basics of light, its physics, and human perception of lighting. So what we always need to include in the design is what are the needs and what we want to achieve with the lighting. What do we want to create a specific mood or a feeling, or and we also need to satisfy the requirements for the vision of people that are the intended users. From scientific aspects, so there's always a scientific aspect and artistic aspect of lighting. From scientific aspects, we must know how much light and what spectrum of light is needed to illuminate specific surfaces. For example, when we illuminate a road, is it good enough to put a lighting pole every 15 meters or 50 meters? And what should be the height, and what should be the luminary? So it all it is all defined on how much light we want on the surface of the road to be present, and what is the maximum brightness variation on the road that is acceptable. And then we can actually calculate what is the distance and what is also the power needed, and how many lighting fixtures we need to put. In the office, for example, we don't want to stumble over something in a corridor, or we want to see clearly on surfaces at desks. People should be able to read different books or memos. In a tunnel also, we want very good illumination, and especially on transitions, when you just enter the tunnel or when you're exiting the tunnel, you shouldn't be blinded by the different brightness levels. So that is the scientific aspect of lighting design. The artistic aspects, or some of the artistic aspects, it is that you want to create a specific mood with lighting. You can also motivate people to be, active or productive, or you can impact their emotions, like make them happy or depressed, or even confuse them with stroboscopic lighting, or relax with very soothing colors and so on. So we can also emphasize visibility or character of a building, and emphasize sharp edges, or make the edges smoother, by using different colors and by using lighting. We can make a bridge appear great and mighty, or we can make a cozy living room by having a warm lighting, like many lamps instead of just one big reflector. Lighting also typically plays or interplays with other hardware to affect all senses. For example, we can combine music with lighting to create a cozy atmosphere, or busy atmosphere, or we can make something look dirty or clean, whatever we want to achieve. Yes, it has also been shown that at hospitals, for example, a lot of green lighting can affect the well-being of patients. So lighting is quite important in building design, and it is not only the scientific aspect, like just put enough light and people will be happy. So there is more to numbers than just having white illumination. Now, so we have to satisfy the function, and that is what meets the eye. We have to transfer the visual information, and that is brightness and color, so that people can see well enough. But we also transfer a concept, and that is for the brain, where there's different perception of depth and brightness, and there's also motion detection. And what's also very interesting is that brain complements and actually affects what we see with all the experience the brain already has. If we don't know color of an object, brain will color it for us based on previous experience. It can also fill some shapes and anticipate things. So it's really a lot of processing of image is done by our brain. And that's something that we can use in lighting design to create some funny effects. I mentioned light and spectrum. So what is white light? So white light, it is a mixture of all possible visible colors combined and with approximately equal power. So if we combine all colors, then we mix them in white. That's what white is. So we can add colors. If we add red, blue, and green, we can get a perception of white. We can, if we only add blue and red, then we will get something purple. And if we add green and red, we'll get the impression of it's yellow light. So eyes, they can also mix different colors. That's also how eyes work in our receptors. In eyes, we have cells that can sense blue or red or green, and then we mix the colors. If we have white light and put filters that only let specific color through, then we can do the subtractive coloring. So if we put cyan filter with a yellow filter, then only green will pass through. Or if we have the magenta filter and the yellow filter, then only the red part of the spectrum will make it through. We can also make a combination of filters that blocks all light, and that is then black, or the absence of light. One of the best white light sources for human eye, that is sunlight. So sunlight has pretty even power at all visible wavelengths. It is not completely even, but when we see sunlight, then it appears white to us. Incandescent sources, so that those are sources based on heat, like incandescent light bulb with tungsten or Wolfram element. They also have very nice and continuous spectrum, which creates a very nice white light. But these are not very energy efficient. So people were looking for different ways to generate light and make it less costly. And these, for example, mercury lamps or sodium lamps or multi-vapor lamps, they have very discrete spectrum. So these lamps, they illuminate not a wide spectrum of colors, but only specific colors, but in a very efficient way. These sources are sometimes good for illumination of roads. For example, high pressure sodium lamps are used in road illumination or street illumination. That's where when many lamps work simultaneously for many hours, then it would be good not to spend too much on electricity bill, but the expense is also that we don't have all colors. For example, we will not be able to see something orange or red under the lighting of sodium lamp. That is where the color rendering index comes into play, because when we specify a light source, then we say how much energy it's consuming, how much light it is emitting, and how good is its spectrum. So that is how good is the color rendering index. If it goes from 0 to 100, 100 that is our sun, and well, we have seen, for example, LED lights, they have color rendering index typical of 80 or so. It means that they can reproduce almost equally well colors as under the sunlight. So there's also only this gap at around 550 nanometers. So we have these different light sources, like old-fashioned incandescent lights. They offer good CRI, but they are poor in economy, efficiency, and lifetime. So they don't have very long lifetime. They use a lot of energy for the light they produce. Actually, they produce much more heat than light, so they're not very handy. Fluorescent tubes, they substituted for some time the incandescent lights, especially in offices, but they have relatively they're not really stable, and they need ballasts, so they cannot just be plugged into our they don't use electricity as it's from the wall plug, but they need some electronics to make it work. And also they're not so environmentally friendly, because once the fluorescent tube breaks, then some vapors not so healthy vapors can come out. I mentioned already some mercury, metal halide, and high pressure sodium lamps. They have also some of the good characteristics are economic. They're economical, but they only emit monochromatic or discrete spectrum light. So they're not very good for illuminating something very colorful. Disposal of these light sources is also an issue sometimes. LED lighting, on the other hand, made a very nice breakthrough because it has good color rendering index. It has very good efficiency, and we can see it now illuminate, living rooms, skyscrapers. We find it in cars, in traffic lights, everywhere. So LED turned out to be a very good choice for a very wide range of applications. We also find LED lighting in roads and tunnels, and whether you need a strong light or a weak light or white or colored light, whatever, then LED is actually quite a good option. Lighting color temperature is also a parameter in describing a light source. And it's actually funny that we call the warm colors, which are in the red, reddish part of the color of lighting. They have lower temperature, that lower CT number than the cold colors, which have high CT temperature. So this is something to do with the maximum illumination, maximum point of illumination spectrum, which follows Stefan Boltzmann's law. You don't need to know this, but it's just counterintuitive that warm colors are lower Kelvin and cold colors are higher Kelvin. Kelvin, that's a measure of temperature. So where do we use bluish light? That is used typically in malls and industrial facilities, in laboratories, sometimes. Bright white around 4,000 Kelvin we use in offices. That's good for reading, for detailed vision in retail. So that's in some shops and showrooms. And warm white light that is up to maybe 3,500 Kelvin. That is what we use in homes and restaurants and places where we don't really need vision that much, but we want to feel cozy and warm and nice. Another part of terminology, another very important units that we need to introduce are luminous flux, that is expressed in lumen. So you have probably seen on a package of a light bulb, it says, I don't know, 720 lumens. It means that is the amount of light that is emitted by the source, that is the amount of light emitted by the light bulb. And we'll jump over the luminous intensity, we'll come to illuminance, which is also very important. It is how many lumens per square meter fall onto a specific surface. So luminous flux, that is for a source of light, and illuminance in lux, that is passive surfaces that are illuminated. For example, we can have 1,000 lumens emitted from a light source, but then we have maybe 100 lumens per square meter that are illuminating a floor or a desk that is, I don't know, 2-3 square meters big in area. I'll just mention that luminous intensity is measured in candela. That's one of the basic units in physics for how much light is going in a solid angle, how much light is emitted in solid angle. This is just to give you an impression of how much is lux, that lumen per square meter, when it's summer and when it's noon and we'll look outside, then surfaces are illuminated by 100,000 lux. And if we are in street lighting or under full moon, it's a fraction of a lux, up to a few lux or lumens per square meter. This tells us also, or shows us, how sensitive our eyes are. So eye can create vision and see at very high illumination and also very, very, very low illumination. So there are many orders of magnitude in this in these examples. So our eyes, they can automatically contract and expand the pupils and control how much light is entering our eyeball and how much light is present on the on the vision cells. When we design lighting, then we should, for example, have this number in our mind in artificial light. In a well-lit office, it's around 1,000 lux. Street lighting between 5 and 30 lux. And in a living room, we need around 100 lux. It means that if our living room is, I don't know, 15 square meters, and we want 100 lux, then we need to emit at least 1,500 lux, but of course, 1,500 lumens. Of course, we emit also on the walls and on the ceiling, so it needs to be a little more than that. But let's look at the lighting in a living room. What do we illuminate and how we illuminate? We don't want even illumination in entire living room. For example, we don't care if part of the carpet is more or less illuminated, but we would very much like to illuminate more kitchen table or surfaces where we use knife or where we read and so on. So we differ between so-called ambient lighting, accent lighting, and task lighting. So I would very much like to see or hear your opinion. What do you think? What is ambient lighting in this room? Will anybody tell me this? Is anybody interested in giving it a try?
Maybe the big chandelier.
The big chandelier here.
Yeah.
So the big chandelier, it has actually the purpose, and its purpose is to illuminate the table well. So I would say that it is task lighting. So it's, well, typically the chandelier would be ambient lighting, but in this specific example, it illuminates the kitchen table and the food that you probably eat. I would say, for example, ambient light, that would be a lamp here. It's making an ambiental light, and a lamp here next to the sofa. These generate general illumination. Accent lighting. What do you think accent lighting would be in this image here? So accent lighting, I would say, for example, illumination of the plant. You want to illuminate specific object with the sole purpose of giving, life to the space. So you want to emphasize, for example, a natural element like a plant, or you want to emphasize a vase with a flower, so that's creating a visual like a feeling for people at in the living room. And task lighting, as we said, so that would be probably the chandelier illuminating the kitchen table, but also maybe lamp here if you sit in the sofa and read newspaper. Maybe nobody reads newspaper anymore. Maybe you read it on a phone now. But if you sit there and knit, then you need to see it very nicely. All right. There's, okay. I just heard that there is a chat with. It looks used for total. Just, All right, there was a question. What is halogen lamp? I didn't see you mention it. I heard about them a lot of times. So halogen lamps, they're these very small spotlights that get very, very hot. They emit relatively white light, and they function on by having very hot substance emitting light. I don't know how to better explain. I think some of the halogen lamps are in the. So this here, it's a halogen lamp. Okay. So there's a question, is lux used for total amount of light emitted by a light source, regardless of the angle? So lux is not used for emitted light. It is used for how much light illuminates a specific a specific surface. Lumen is used for total amount of light emitted in all angles, in all directions. Lux, that is lumens per square meters. So how many lumens per square meter touch or fall on the surface? And we have the small lamp on the shelf. Yes, that's also correct. I mean, in case of flashlight that can change focus, if we move the lens, does the lux change? Yes, lux changes when you focus light. So instead of spreading a specific and fixed amount of lumens on a very big surface, you can focus it and put all the lumens on a very small area. It means that more lumens per unit area will illuminate this small surface. I think I answered the questions. I'll just come back to the presentation. Let's see. All right. How many of you can see a square in this image? And how many of you can see a circle in the image?
Well, I can see both. Is that a good thing?
Me too.
It's a good thing, yes. It means that you have good vision, or your color vision is good. There are around 10% of people cannot see difference between brownish and greenish objects. So if you do not see a circle, then then you could be slightly colorblind, or if you don't see a square, it's just different receptor cells are responsible for seeing these colors. This is meant to be a small image for a small break. So is it fine that we take a 5-minute break now? All right, so we're back. Is everybody back in place?
Yes.
Goody. So we had a small introduction on lighting, and unfortunately, that is about it. We concluded that LEDs are really versatile. Now we need to learn how to control LEDs. We control LEDs by electronics. So let's try to see. Okay, we'll start with a small introduction to electronics and with specific focus on how to control LEDs. Most of you have probably heard about resistors in a circuit, so that they look something like this in the lower right part, and they're like international standard sign in a circuit diagram. It's on the upper right. Resistors are measured in ohms, or resistances are measured in ohms, and we have common values like 100 ohms or 1 kilo ohm or 10 kilo ohms. So the small k, that is for kilo, it means 1,000. The zigzag line, it's mostly used in the US. Rectangle is mostly used in EU, but actually the zigzag is more correct because the rectangle, it represents not just resistor, but something called impedance. So we prefer the zigzag. Resistor, it limits the flow of electric current. So if we have a positive electrode on one side and negative on the other, then electricity or current would like to flow from one end to the other. If we have high resistance, then only small current will flow. If we have small resistance, low resistance, then a lot of current will be able to flow. You can maybe make a parallel with water flowing through a pipe. If you squeeze the pipe, then you make a resistance. You resist to the water flow. If you squeeze it a lot, then it's a high resistor or high resistance, and not much water will flow. If you only squeeze it slightly, then more water will flow. If you increase the pressure, that is the voltage, then more water will flow or more current will flow. And if you decrease the pressure between the squeezed and between the sides of the squeezed part of the pipe, then you reduce the amount of water flowing there. So this is like water analogy. I don't know whether it works. For me, it's better, current analogy for the water. Capacitor. So what is a capacitor? That is a component that can store charge, electrical charge. Capacitor or capacitance is measured in farads, and typical capacitors that have very small capacitance are in microfarads or nanofarads. The sign for capacitor is just two parallel lines most often. So what is capacitor? That's like a bucket for the water where we can put the charge, and then we can use that water later in the circuit to discharge it. Timing circuits, for example, they use so-called RC circuits. It's resistor capacitor circuits, where we can measure time with them. So we can first put switch in position A, and then this is a source, or this is a voltage source. So current will flow through the resistor into the capacitor. If we have very large resistor and very large capacitor, then it would take a lot of time to fill the capacitor. And then when we put the switch in position B, then it would also take a lot of time to discharge the capacitor. If the resistor is small and the capacitance is small, then the capacitor will be filled with charge very quickly. So the red line here, it shows the charging, and the blue line is discharging of capacitor. And the time it takes to charge and discharge, it depends on the product of R and C. So this is actually how first clocks are made with RC components. So these are good for timing circuits. We're not going to use them. We use today microcontrollers, but it's nice to know that RC circuits, they have time constant. When you multiply resistance with capacitance, you actually get time as unit. You get seconds. All right. Next component we're going to look at is the light emitting diode, or LED. It emits light of a specific wavelength or color. So all LEDs, they have relatively narrow spectrum. So they can either emit blue or green or red light or yellow light. They don't emit very broad spectrum. So we use different tricks to broaden their spectrum to get white emission of light, but there is no white LED. The white LED, it is a combination of several emitting structures. So it can be, for example, blue light, blue LED, that is at the same time not only emitting blue light, but exciting a fluorescence layer that fluoresces in yellow or red colors, and then all these combined, they appear to be white. Now, when current flows through a diode, it has to flow from anode to cathode. So current can only flow from plus to minus. If we reverse the diode or reverse the voltage, then no current will flow. It will simply block the current. So we cannot plug LED in a circuit like in any possible polarity, in both possible polarities. Like, for example, incandescent light bulb. The incandescent light bulb doesn't really care whether current flows from left to right or right to left, but the diode does. When current flows through the diode, then the voltage drops across the diode. And typically, you can find it always in the data sheet for the diode, but it's typically from 2 volts to 3 volts or 3.5 volts, depending on what color it emits. And in a small LEDs, then the current is typically maybe 5 to 20 milliamps. There are also LEDs with much higher power. There are LEDs that illuminate building blocks, and they can consume 15 amps. That is 1,000 times more than this small LED. But we're going to play with these small LEDs that can run on microcontrollers and that are very, very safe. So let's just have in mind that the current through a typical LED is, I don't know, 5, 10, 20 milliamps. that cannot harm you. Power supplies are also very important in electronics, so we need to supply power to our LED. And this can be battery packs, it can be adapters, AC/DC converters. So the current from wall plug, it is alternating current AC, and current which we supply to LEDs, it needs to be direct current. So we need to convert from AC to DC, and we also need to come to the right voltage level. There are also variable power supplies or fixed power supplies. There are many ways to supply power to our LED. Tools in electronics. So we have breadboard. That is the whiteboard with a lot of holes where we can put different components. Power source, here we have a battery that supplies power to the circuit here. And we also, the most important tool what we use is so-called multimeter. And I also have one here, if you can see it in camera. There are also much more advanced tools like oscilloscopes, network analyzers, but we're not going to use those. Those are used when we look dynamically what happens with voltages and currents. And this is the only formula I promise that we're going to go through this evening. It's Ohm's law. It just tells us that the voltage, it equals current times the resistance in a circuit like this. So if we have, for example, 5 volt voltage supply, and we connect 100 ohm resistor through here. So what is the current that flows in this very simple circuit? You need to rearrange the formula here. So will anybody tell me? So the current will be equal to voltage divided by resistance. So if we divide 5 volts with 100 ohms, then we get 0.05 amps. Ampere is the unit of current. So 0.05 amps, that is 50 milliamps. That's how much will flow in a circuit like this. So what happens if current, what happens with current if we increase voltage? If we, for example, instead of 5 volts, set 10 volt supply, then current will be 10 volts divided by 100 ohms. So it will be 0.1 amps, so for 100 milliamps. So if we increase voltage, we will also increase the current flowing here. What happens if we increase resistance? If we increase resistance from 100 ohms to maybe 500 ohms, then the current will be 5 volts divided by 500 ohms, and that is 10 milliamps. So if we increase the resistance, intuitively and logically, the current will decrease. Now, why is this important? Because when we want to calculate in a circuit with an LED, we want to make, typically our voltage supply is maybe 5 volts, and we want a current of 10 milliamps. And how can we make the current 10 milliamps, if we know that voltage will drop 2 volts across the diode. If the voltage drops 2 volts across the diode, it means that the voltage will drop 3 volts across the resistor, because we have 5 volts in total. So 5 volts is here, and then 2 volts is here. It means we dropped 3 volts across the resistor. So we have 3 volts divided by 10 milliamps. 10 milliamps is our desired current. We need a resistor of 300 ohms to make the current right. It doesn't really matter if you put 300 ohms or 100 ohm or 1 kilo ohm. It's just important that you put some resistor in a circuit with an LED so that you protect the LED from too high current that will burn it, or you also protect the source, which can, if it's battery, it would be exhausted too quickly if you don't put a resistor, if you don't limit the current, or you can also burn your adapter or damage battery if the current is too big. All right. So let's list the components we looked at. It was resistors. We use them to protect LED, that is to limit the current flowing through LED. We use them for so-called voltage dividers, current limiters, pull-up resistors, capacitors we use for timing circuits, for noise filtering, for energy storage. We're not going to go into details like here. Diodes, they are very useful because they allow current to flow in one direction only. And if they are light emitting diodes, then they also shine. That's really great. And we're thankful for them to do that. We didn't mention transistors in this presentation, but transistors, they are used to control, very nicely, control current flow. And what microcontrollers do, that they possess millions and millions of transistors. So we're going to use microcontrollers to control current flows, to read inputs from sensors, perform specific functions. So microcontrollers are the central part of controllers that control lights. Lights can be turned on, turned off, but they can also be made to blink or to fade or to just blink randomly, or how we control lights and also their colors and their brightness and everything. It is through microcontrollers. We can write very simple codes and make the lights or LEDs perform in a way that we want them to. So microcontrollers, they are programmable circuits, and it makes electronics design with them extremely easy, because we just write code what we want an LED, for example, to do, and then microcontroller takes care of it. For example, in this code to the right, we define that one pin of a microcontroller will control an LED. It will be an output, and we write to this output that it should be on, wait for 0.7 seconds, and then it is off. And then we wait for 0.3 seconds. And then the loop will just continue making the diode blink. So it's very simple. And if you make interesting projects by yourself, then it can also be very, very fun. And it's also very simple, and it's especially simple nowadays when you can just ask, for example, ChatGPT to make you such a short program, and you just describe, I want, this to blink, the other one to fade, I want different effects. So your imagination is the only limiting factor there. Coding is done on computer in a universal Arduino Arduino environment, so you can download for free the Arduino environment, and you typically start a program by assigning what is an input and what is an output. So every controller has some pins to the left and right here, and then these pins are numbered. And you would typically say, so start your program with saying mode of the pin or pin mode, LED, that is the number 13. So pin number 13 should be an output. That's what this line says here. Then we have loop that just repeats commands. And commands, they are, write logical high, write logical low. It means turn on and turn off a specific pin. And if you connect an LED to this pin, then it will blink. So we're going to go through most important microcontroller like Arduino or ESP commands. These are structure commands, digital input output, analog input output commands, and timing command. So every program, it needs a setup and loop. So I'll just go back here. So we have setup, where we tell the microcontroller which inputs and outputs are going to be used. And there's loop, which is executed until you switch the device off. So it's just endlessly executing the program. So this is the structure commands. Digital input and output commands, they are typically to write and read from digital input output. So we can write a value. For example, we want to set the pin high or low, so that we want to switch something on or switch something off by telling what pin number and what value. So if I say digital write 10, high, it means that I'm switching on pin number 10. Digital read, it reads a value. So this is an input. Read is an input and write, it is an output. When we read from a pin, let's say pin number 22, then what we read is either high or low, or logical 1 or logical 0. So this is for digital inputs and outputs. And for every digital I/O, we have to assign what kind of pin we want to have. Like we can say pin mode 10, output. It means that pin 10 is an output. We can say pin 2 is an input, or whatever. Analog read and analog write do absolutely same thing. So read reads a specific value from pin, but the value is not either 0 or 1. It can be an quasi analog value from 0 to 2023. So it can digital value, it is just on or off. Analog value, it can be like a temperature. It is graduated. It is gradually it can attain a value between 0 and 1023. So it's not either or. The same goes for analog write. So we can say to which pin we want to write a specific value. For example, if we want an LED to dim, then we will assign a specific pin like an analog output, and then we will make the value smaller and smaller. It means that the current will be lower and lower in the LED, and it will shine less and less and less. And timing, it's also very important. It just makes a delay. So we say delay 1000, it means wait for a second, wait a second. Sometimes electronics is simply too fast for people. So for us to really grasp what's going on, we have to make everything slower. So we need to put a lot of delays in our programs. So let's sum up. We have resistors. With them we control current. We use breadboards to build and test our circuits. We can build LED dimmers, timers, simple filters. If you learn this, then it's really foundation for your electronics, and from this you can build further, and you can build very interesting projects in very, very small, relatively small knowledge of electronics. So it's very basic what you actually need. And microcontrollers, the central part of this of the design, they make it possible to construct functional electronics in a very fast and simple way by just writing code beforehand. If you wanted your diodes to blink, you had to build RC circuits with a lot of calculations in it. And if you want to change the delay, then you have to change the entire circuit. Right now, with microcontrollers, you just say, well, delay is not 1000, but now delay is 800, and then it blinks faster. Do we want a 5-minute break now? I think it's a good
Okay.
time to make a short break before we go to microcontrollers. So I'll let you digest this. Okay. All right, we're back. Is everybody with us again? Good. So we're gonna continue with looking specifically into the microcontrollers and looking at board overview. So the most famous microcontroller board in this context is Arduino, and it has many different versions, but Arduino Uno is probably the most famous one and the one that one can start with. Well, you typically on all boards, you have a reset button, you have USB connector with which you connect to your computer. You use your computer to write code, and then via the USB cable, you upload a program into the chip, into the processor. You can use power barrel here to supply power to the Arduino, but you can also use USB connector to supply. Depends on how much power you'll supply. There are some pins which are digital IOs only. Some pins can be both analog and digital. Some pins are digital only. Then there are also some specific pins which are for communication. So you can see, for example, here TX, it means the transmit pin, and RX, it is receive pin. So you see the arrow is going into the board when it's received and out of the board when you transmit information. We are also Sorry, I lost you for a second. I lost my connection. I apologize for this. I think we can just continue from where I stopped. We spoke about the microcontrollers used, and we typically use Arduino, but we can also use slightly cheaper and smaller microcontroller with a screen on it integrated. That's called LilyGo. LilyGo looks like this. When you look at it from top, it has a USB connector. It has some push buttons to the left and right, a reset button, and we can read what are the power pins. For example, we want to supply something from the board. We can use some so-called ground and power supply pins. Light green, they can be both input and output. So light green pins, they are input-output pins. We have just a few strapping pins, wake up, RTC wake up, that's not something that we're going to use. And dark green, they are input only. So these pins here, they can be used only as input. Let's see what we hear now. Okay, great. We had some issues with the power since, but we're back. Good. So, for example, we can use pin, I don't know, number 32 as both input and output to issue a command for powering an LED. And we can use dark green input only, for example, 36, to read value from a specific sensor or whatever we want. We're not going to use communication pins, but these two are used for communications. And DUC, it says it's for digital to analog converter. SDA and SCL is serial data and serial clock. So this is the communication pin. So let's understand the concept of input and output. So input, that is a signal going into the board. So that can be signal from a button, from a light sensor, from a temperature sensor, and that is what we read. So we read an input. We can either make a digital read or an analog read. Digital read will give us discrete value, either 0 or 1, either that's low or high. Analog read, it will give us it can be a range of values. It can be many different values. For example, if we want to send temperature, well, we can say it's either hot or cold, but we would really like to see whether it's 18, 22, 25, 28 degrees Celsius, whatever. Output, on the other hand, that is what the microcontroller is telling to the outside world. It is sending signals out of the board. It can control LED. It can switch on or off a motor. It can control a buzzer with an output or a so-called relay, that is switch control. And to outputs, we write a command. So we can either make a digital write or an analog write. In a write command, we always say to which pin we want to write a specific value. When we read, we just say from which pin do we read. Some microcontrollers cannot really handle analog values, but there are ways to go around analog values using digital values only. And that is where we use so-called pulse width modulation. So pulse or PWM. PWM signal, it represents, so the orange signal here is an analog value. It is represented by PWM by the length of the high. For example, if we have a high value, then the logical one will be on for a longer time than when the value is very low. For example, value is quite low here, and we have this small spike just for a very short time. If we take an average of the black signal here, we will get something close to the orange here. It's called pulse width modulation, and we modulate or change so-called duty cycle of a light. So why is this very useful? Well, it's useful because LEDs, they like much more to be controlled with pulse width modulation signals, because LEDs, they either like to be on or off. That's when they're efficient. If they get low current, then they can change color. They cannot be very stable. So LEDs, they really prefer PWM signals. Duty cycle, it means for how many percent of a cycle is signal on. For example, 50% duty cycle, it means that half of the time the signal is on and half of the time signal is off. 75% duty cycle means that 75% of the time signal is on and 25 it's off. Likewise for the 25% duty cycle. So this is so-called PWM. Analog inputs, we have typically 6 analog inputs on Arduino, and these pins have inside the chip analog to digital converters, or ADCs. ADC can read an analog voltage, typically between 0 and 5 volts, and then translate it into a number from 0 to 1023. 1023, it's because it is a so-called 10-bit ADC. So the analog value, which we see as a dashed line here, it is converted into a digital signal, which is a little bit quantized, so that it cannot attain any value, but it's a little bit quantized, but it's much better than just having 0 and 1. All right. We have power supply pins on the board, and if we go back, for example, here, we can supply power from the board. We can supply 3.3 volts to some sensor which uses 3.3 volt supply, or 5 volts to some motor which is using 5 volts, or we can use we can supply from our board power to other auxiliary equipment. Not much power, but a little bit we can. All right, so in electronics, we have typically, some sensors or actuators like push button or variable resistor or photoresistor, and the type of input to the microcontroller is, for a button, which can be either pushed or not, it's digital input. Variable resistor. It is an analog input because we input an analog value to the microcontroller. Also, the photoresistor, it means a resistor that is sensitive to light. The more light comes to the component, the more or less resistance it will make, so that we can sense how much light is in the room, so you can have ambient light sensing with such a component. Relay is it's a switch, so we can, with a very small current, make switch of a very large current. We'll probably not use these. Then there's temperature sensors, flexible sensors, trim pods, RGB LEDs or LEDs. So all these have specific type of input or output via which they can be controlled or interfaced with a microcontroller. So we'll make some examples of codes. We'll look through some example of codes. I also have a microcontroller here next to me, but I think because I will have to switch on the computer because we had some power outage. But let's look at the codes. For example, we define pins. It means constant integer. We call it button pin is equal to 0. So this is whenever we write button pin, it is the same as if we wrote 0. Or if we write LED pin, it is the same as we wrote number 32. So when we write in the setup pin mode button pin, it means that pin mode of pin number 0, it is an input. And pin mode of 32, it is an output. Then we can test whether the button is pressed or not. So if the button state is low, then we will write on the LED pin high, else we will write on the LED pin low. So what this program does, it reads simply the state of the button, whether it's pressed or not, and lights the LED when it's pressed and doesn't light it when it's off. All right. Example of analog input code, we have a sensor value. We initiate it to 0. And we read analog. We make an analog read from A0, and we print or we write down the value of the sensor value onto the serial port. So we send on a serial port the value of the which is read, and then we wait for 0.1 seconds because otherwise we would just send values too quickly. So it says here it reads an analog value and displays it or sends the value on the serial line. We also have a code example for PWM analog output. I think we are approaching the end of the lecture, so we're not going to go very deeply into this. So loops and counters. So loops in Arduino, we can have a for loop when we know the number of repetitions. It's a fixed number of repetitions. For example, we say from integer I is equal to 0 until it is as long as it's less than 10, and in every cycle it increases by 1. And then from this parenthesis to this parenthesis, when this is executed 10 times, it will simply continue the rest of the program. While, we can just say while and then use these parentheses, while some condition is satisfied, then as long as the condition is satisfied, for example, as long as a value of a specific sensor is 0 or 1, then you do the loop. When it's not, then you continue the program. And you can also do a so-called do-while loop. Counters and timing. I think the most important command generally in timing is the delay command. We'll not go now into other commands. So in summary, how do we make a program for our Arduino? We first configure the pins. We read values, execute a program, and write values. So the microcontroller, it reads the state of different devices, and according to these states, it issues commands. And then we use loop for continuous execution. And yeah, it's important to fill always delays in the program so that they don't use, so that they don't evolve too quickly for a human. And what's also very useful hack, I think I mentioned this, AI is very good at writing Arduino codes or ESP codes for beginners. So it's very fun to use Arduino because you don't struggle with the code and something is not working and you are missing the semicolon, or you forgot a parenthesis, or you don't know how to do this and that. You just ask ChatGPT to help you a little bit, and then you can have a very, very good code without too much trouble. So the point was to go through different laboratory exercises, but we don't have so much hands-on here. I'll just show you, for example, this program which makes the LED go high and low. I'll just switch my video to USB camera. And I'll allow the video. So I have my ESP controller here. It is supplied with USB cable, and on another board I have from pin 32 signal via protecting resistor into an LED, and current can go back to ground here. I'm not really using standard color coding in these wires, but you can see that the LED is blinking. It's half time on, half time off. I think the period is 1 second. I'll switch back. Okay. So it is executing this program here. We have an LED on pin 32, and then, well, here it says delay is 700, 300. I think in the actual program I uploaded, it was 500, 500. Okay, this is an example of code where we have a fading effect of an LED. I also made a project called Moody Diode, where it can either be calm or excited or nervous or sleeping. So I have a diode that blinks with a very slow, calm rate, or excited, it pulses very quickly, like tick, 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 tick. Nervous, it is a random, it is pulsing with random period, and sleeping, it's very, very slow. So this is the project Moody diode. It has modes 0, 1, 2, 3, and blinking interval can be 800, 100, random. And unfortunately, we're not going to upload it here. We're finishing in 4 minutes. And I was also going to ask you to experiment with different codes, and we can have random delays, like for how long time an LED will be on, and for how long time it will be off. And yeah, we can create actually different feeling by just making the diode blink differently. And that's only one diode. If we have like 10 diodes or 100 diodes, then we can make like a bouncing light, or fading and gradually increasing light on different, also using different colors, LEDs. Here I only have one blue. I had one group of students who made like a ambulance or police lights, and with just two colors and changing the pattern of lighting, you can see that it's different situations from daily life. It was funny. Everybody else was guessing then what is this and what is that now. So all right. So I will thank you now for your attention, and ask you whether you have any questions.
No questions so far.
All right.
So anyways, thank you everyone for joining. I want to share with you a few very useful links. So I'm just gonna place that in the chat. Oh, just a second. I exceeded the amount of... Okay, here and here. I'll send you that, guys, in the email after the event, but I highly want to recommend you this British artist, Richard Yacht, that works with light, and he has a really great book on lights for designers and architects, and pretty great website where you can check his work. That's the first link. And a very nice video where he shows he works with illustrations and animations, and he's shaping like different kind of lights and like tells you like how the lighting actually shapes the entire storytelling and feelings, and like how we feel about characters, and like I don't have to create drama and all that. So it's really great. It's 1 hour and a half, so it's takes some time, but it's very entertaining. Yeah, and then I just left you some links of famous artists that work with lights, and some upcoming events in 25, like recent events or something that is coming in 2026, just to check some artistic work of artists that work with electronics, photonics, lighting, and all that stuff. So I hope you find it useful. And yeah, that's it for today. Thank you for joining, and thank you, Emir, for today's lecture. And see you see you tomorrow, some of you.
I hope I didn't bore you too much.
Yeah, thank you, everyone. Thank you.